It's a little bit of feedback. Good. So today will be about what subject you're probably familiar to most of you is the beauty and strangeness of two-dimensionality. How everything is different in 2 dimensions. So we'll start from looking again at Navier-Stokes, well, let's say at earlier equation. So we have a vector field, and it's incompressible. Let's say my density is unity, but so if I'll take its curl, so I'll just take a curl of this equation. This would be omega, which by definition is a curl of V. The right-hand side disappears, right? So you just, there's 0 in the right-hand side. And then you can show that it's, you can present it in the form omega, which is in 2 dimensions. Moreover, you can present V because it's a 2-dimensional vector, so you can introduce what is called stream function, namely that you say that this would be d psi dx minus d psi dy, vx, vy, vx. So this vector you present like this. So essentially, your right-hand side has the following form. It has a form of a Poisson bracket. What stands here is d omega dx, d psi dy, minus d omega dy, d psi dx. That's your bracket, omega psi. Now it immediately tells you that this is essentially the equation that you may write like this. All right, so this is just every piece of a fluid conserves its vorticity. So now vorticity is what we call Lagrangian invariant, right? Which means that as you flow, this is because the 3-dimensional effect when you can take a vortex and you can stretch it in this direction and expand it in this direction, fluid is incompressible. So if you compress it, you also stretch it. And that means that because the vorticity flux is conserved, that local vorticity increases when you come. In 2D, you cannot do it. It's just incompressible flow. So every element carries its vorticity. And it means that any integral of vorticity or any function of vorticity is conserved in an ideal fluid. And in particularly, a totally sign definite integral is conserved. Apart from kinetic energy, and this is a situation which the whole classes of system are like this, where you have 2 quadratic invariants. This is, let me remind you, is this quantity, right? And it immediately leads to a very dramatic consequences, namely to the existence of 2 cascades, and not only 1 cascade. And one may argue it in a very simple way, just by pure algebraic reasoning. So let's say I'm looking at it in K space, and say that at some K1, I have, something working. Fun just brings energy. So I have an input here of energy E1. This is in a sense, it's just V1. This means K equal to K1. That's a kinetic energy that I bring, and with it, I somehow bring K squared E K1. That's my omega 1 squared. Okay? And now I am saying, okay, there is no viscosity acting here at this scale. There is somewhere viscosity at a very large K. And so I assume that I would somehow have a cascade which would bring these things towards my dissipation. Let's call it K3. And let's call it this K2. I would rather arrange them according to, because in a moment it will be clear that I will need a K1. So what I would say that if I have an input E2, then, and if I happen to have another region of dissipation at K1, that will be also added here. And the same must happen to the squared vorticity so essentially I am using conservation of these two quantities in such a kind of simply scale is a wave number in a sense. Okay? So I'm assuming that let's say, what I'm talking about is I see a very simple reality. We have an experimental apparatus in which we have a very thin layer of fluid which models two-dimensionality. We put magnets of the size of 2 pi over K2. In a sense, there are like 9 millimeters magnets. There are 100 of these magnets. And when we run current, we input energy into vortices of this size. Okay? Then we see a lot of turbulence in the system. So there are very, very small scales where viscosity is starting to be important. But also, in a moment, we realize that you cannot satisfy this equation without this. Right? If E2 is equal to E3, this is definitely not equal because K3 is much larger than K2. Then you need this thing. Okay? So if you now substitute here K3 squared A2 minus A1 plus K1 squared E1, then immediately you'll get this K3 squared minus K2 squared. I'm taking this E2 is equal to, and now I'm bringing everything with A1, this and this. So I have K3 squared minus K1 squared of A1. And I may divide by this. And what I obtain, the following relation. It's a very simple algebra. So what I'm seeing that when my K3 is very large relatively to K2, it's also very large with respect to K1. So I can neglect both of these quantities. And this is unity. So all my energy is absorbed here. By the same token, it's quite easy to show that when I derive then all my K squared E would go into this. And this is a two-cascade picture, was invented by Robert Reichman, and independently almost, but I mean derived by Zakharov just as a formal solution of equation for waves. It's a very, very frequent situation when you have two quadratic integrals of motion. For example, any wave scattering conserves the number of waves, and it also conserves energy, so you have always this double cascade situation. But in fluid mechanics, there is a whole family of such things. And in last, I don't know, 60 years, it's more or less, and they all are two-dimensional, and they look like this. They are essentially has a form dA dt equal to 0, which means dA dt plus v grad A equal to 0. And A is a scalar. Vorticity in two dimensions is pseudoscalar. The difference is that V, which is always expressed through the stream function, but the relation of a stream function and A could be different. And in this particular case, for Euler equation, omega is the Laplace of psi function. But generally, in this class of models, they were kind of introduced one by one. Now we look at them as a family, but we say that psi is gradient, kind of somewhat symbolically, can write it in the power m of a. So just a of psi. So m equal to 2 is Euler on Navier-Stokes if we add viscosity. M equal to 1 is what was called surface quasi-geostrophic. It's a model in which you have a rotating inhomogeneously heated fluid, so you have a Coriolis force interacting with buoyancy. So buoyancy creates some kind of motion. You can have m negative, m equal to -2. It's a very fast rotating fluid or very strongly magnetized plasma. It's called Hasegawa-Mima or Charny-Obukhov equation. So there is a whole enchilada of some such model. But they all have the same form. This term is psi a, Poisson bracket, which means that they conserve any power of a just by virtue of this equation. So they have a squared integral dx dy conserved, but they also have integral psi a dx dy. This is v squared for Euler equation, because this is Laplacian of this, so you can put it and you find out this is v squared. So there is a whole family, and they all have inverse cascades. Okay, so for a moment I will talk to Euler and show you some great surprise that we found for Euler, and then we'll come to this set of models and we'll find out that each one of them has it also. What when we look at this new beast, which is a inverse cascade of energy, scaling-wise, it's the same, right? When we ask what would be the scaling of delta V cube, like let's say, longitudinal component, we found again that it's just epsilon times r, measured at a distance r. You can just derive the same equations that Kolmogorov derived in 3 dimensions, in 2 dimensions. You actually don't know what sign of it, but sign is different, which you kind of measure experimentally. And then surprisingly, we find out that if we look for any moment, it's just what we call normal scaling. And there are factors here. We cannot compute them, and we don't know if they are universal. They aren't changing much there aren't that many experimental realization. In some sense, because this is a cascade generated by small scale driving, this most likely in some sense universal. But if you ask about the probability distribution of velocity differences measured at a scale L, then this is indeed scale invariant. It's homogeneous, so it's a function of a single argument instead of 2 different arguments. Okay, and nobody ever derived it. This is just an empirical fact. There were many returns to it and checking it in many different forms. It holds in the sense that this probability distribution is self-similar. Nobody knows why. Nobody can prove it formally. I tried to prove it from a Lagrangian viewpoint, trying to look at the motion of fluid particles, and I'll return to it a bit later. But what we then found out, it's totally unexpected things, that somehow for purely religious reasons, when physicists see a scale invariance, he starts asking for more, and more is usually conformal invariance. And conformal invariance is a kind of, at least in 2D, it's a very powerful infinite dimensional group. It tells you that not only you can take your picture of your fluctuating field and rescale it, you can do it like this. You can rescale it in one place, and then the degree of rescaling can smoothly vary along the coordinate. In a sense, spoken a little bit more formally, if I have a domain D, and and I have turbulence here generated by this type of a small scale forcing somewhere at the scales much less than the size of my system. And I have different points. And I have some measure, namely some probability distribution related to these points Z1, Z2, Z3. Could be the statistics of velocity difference taking this minus this minus this minus this, something like this. Or take vorticity at this 3 point and ask for any probability related to the vorticity field in this 3 field. So you have some family of measures with this generally how many points you want. But then you can always map a domain into D by some function. And so you call it D prime. And there are images of these points under this map. They somewhere go. So you would have mu D prime, Z1 prime, Z2 prime, Z3 prime. The statement is the measure is conformal invariant if this is equal to this. So in a sense, whatever probability you compute here will be the probability that you would compute here, just doing turbulence in this domain with the same forcing. That's the important thing. Because the forcing which gives you, yes?
And this is only valid for one-to-one mapping. I mean,
it's only into D. Yeah.
I mean, one-to-one mapping means 1 point to correspond to 1 point in D. Right?
Yeah. If you have domain to domain, it's more or less you have a single map which gives. This means that for every point you have a 1 point over there. Okay. Everything is analytic here. Right? Domain is analytic here. Probably one can do it with corners and with some other idiotic things, but let's say like this. Okay. So this is a very powerful thing, because if you know that your statistic is conformally invariant, it means that many statements on correlation function are very, very restricted. So your set of correlation function is very restricted, because a conformal map is an infinite dimensional group, right? So this invariance. And all this suddenly brought a very old and very mathematical subject into it, which is called Löwner revolution. So let me now explain you what is Löwner revolution. Löwner. I guess it's after he ran from Nazis to US. Its name was spelled differently, and he was Karl, and then he turned into Charles. This is the works that I'm going now to tell, what is called Löwner revolution. It's 20s, late 20s. Okay, but after 40s he lived in the United States. So what was his idea? He said that there is a way, and this is pure geometry. Well, geometry and conformal analysis. He says that there is a way to encode a curve in a half plane in a very, very particular way. So let's imagine that I consider a half plane minus this curve. The curve, this is gamma. I can call it gamma of t, and t will be not time. It will be internal parameter along the curve. Okay? So as my curve propagates, so consider it as a slit. So just you consider half plane without this line. Well, this is still a domain, and the Riemann theorem still works. So you can map it by some g of t into just half plane. Namely, you kind of absorb the slit into the boundary. That's what we do, usually in elementary conformal analysis, we usually absorb something trivial like this or like this. But you can absorb any curve, which means that now as you move along the curve, there will be only singularity of this map. And this is the tip of this curve. And because it's on the boundary, it must be mapped into the boundary. So somewhere we have this is an image of this tip, right? And it's on the boundary of our domain, and we call it psi, and it's also a function of t. So as your curve propagates, your image of the tip somehow moves. And it's a very powerful idea, and mathematicians used it many, many times. That means that you can encode a shape by one-dimensional law of motion. So this function, psi of t, tells you everything you want to know about this curve. It just encodes its shape. Technically, what Löwner derives that if we now impose a simple condition on this G, because apart from saying that you're working with half plane, you need to put another boundary condition. It's always you want to define a map. So we say that when z go into infinity, G of z goes to z, namely that very far away from your curve in just identity transformation. But it will be next correction to it, and we this coefficient, this would be this kind of our time over here. This is in a sense what kind of normalizes this curve, right? This kind of next term. And then the other term would be smaller correction in 1 over z squared. In this case, the equation is very beautiful. It's called Löwner equation. It has only one singularity, so apparently it's and I guess 2. It's Löwner equation, okay? And it, as you solved it, which means that this is a known function. It encodes your curve. If you solve it, it gives you the curve. It gives you the map, which essentially maps your half plane into this half plane minus this slit. So that was an idea. And this Löwner evolution was used for 80 years for different things. And then another mathematician, Aded Schramm, our Weizmann Institute. So as life has it, we started at Weizmann at about the same time, and we knew each other. And he even came to me and asked me about something about turbulence. I did not know that he was doing this beautiful thing. He died in a mountain accident some 10 years ago. So what Aded Schramm suggested is to look at this Löwner evolution, assuming that this is the Brownian walk, right? Just a random Brownian walk. In a sense, let's now, and he was a probabilist, and this is now, as usual, it's a very powerful thing when geometry means stochastics. So first of all, for very simple psi, for example, when psi is a constant, then the curve is just a straight line, right? As you start moving here, this line kind of moves. But what happens if this is the Brownian walk? Namely, just randomly moves along a line, okay? Now, if you take a random walk, essentially you're saying that your driving function is determined in a continuous limit. It's proportional to delta function of t. It's delta correlated in time. And there is some factor over here, which is, I mean, everything is kind of dimensionless. So this is just a dimensionless number because we already kind of normalized everything by t, which is a coordinate along my curve. And then you start looking into classes for which different kappas give. And the big surprise for physicists at this point was that everything we knew about two-dimensional critical phenomena was encoded in this kappa. It's all about lines, right? So in physics, we had lines before. We may consider critical Ising model, for example, and ask what is the boundary between positive and negative spins, which means the boundary of a domain. You have a domain with positive magnetization, and another with negative. And it's a random curve. And then it was shown that it corresponds to kappa equal to 3. Then you may have a different type of a critical phenomena. For example, you look at a landscape. It's two-dimensional landscape, okay? And you start filling it with water. It's called percolation. So you actually consider some kind of a random function of x and y, and you consider isolines on this function. as you increase this constant, at some point, you'll be in a situation where more or less the probability of hitting an island and sailing along the sea, let's say you fill it with water. So this is your water, and this is your. So the probability to go somewhere sailing and the probability of walking on islands is the same. If this function, which has a mean value 0, and it's a short correlated function, you of course can show that its value h equal to 0 is a critical value, and then you have what is called percolation cluster, namely a random curve, which corresponds to this line of a boundary between water and Earth, and it's kappa equal to 6. And all these miracles, and so naturally physicists were fascinated by this. This is this centuries of something. All this big buzz happened around, I don't know, 22, 23. Yeah, exactly. I was in Princeton on sabbatical, and Perelman came with his work, but also John Cardy was giving a course on this, and I was asking my mathematician friend, what should I learn, this or that? Actually, now I understand that both. They said, no, you learn this. It's called now SLE, Schreier-Löwner evolution. And they were right, they were more immediate. So what it has to do with turbulence, from what I told you before that. So when we were, because now what it essentially tells you, something very simple. It gives you a very powerful technical tool, very empirical. So you have a random curve. OK, you can download an algorithm, which there are now many. Back then, when we did it 15, 17 years ago, there was only a few, but they were still working. So what we took omega equal to 0 line in our two-dimensional turbulence in the domain of inverse cascade. Now there is just a line. For physicists, it's a very important line, because omega positive is called anticyclone. When you look at Earth's atmosphere, it has a rotation, right? So if you have locally your air rotating in the same direction, namely that the omega has a positive projection on the planet axis, it's called anticyclone, and it's where it's a high pressure, and it's where it's a nice weather. So when omega is negative, it's where you have cyclone, where is negative pressure, namely there is an opposite rotation. So you have a height of atmosphere is locally lower, and so the boundary between them, it's practically a very interesting point. This is where weather changes. Okay, so in a sense, it's not only for purely mathematical reason. And then what you do, you just kind of arbitrarily, at least what we did, in all, and we did it in a very non-rigorous way, and then more mathematically oriented people sorted it out in a more rigorous way. But we just kind of cut our turbulence plane somewhere, say, OK, here is our curve. We divide it into straight pieces, small straight pieces. And we just built numerically this function, absorbing, because we know what is a standard map which absorbs any straight line at whatever angle to it, it absorbs into it. And so we built all this G.
Can I ask you?
Yeah.
What about the initial conditions?
Initial condition is that usually in our case, you start from this point, which means that your G at 0 is Z. It's an identity transform. Okay, it's defined everywhere. Okay, so G is Z, and then you just kind of do a small piece of it, and then you change it a little bit around this domain, very far away still Z, and then you do it step by step, and you get. Eventually, you get your Z, zeta1, zeta2. It's a discrete set because you have a discrete set of it. And then you just check if it's a one-dimensional random walk. There are very powerful algorithms which check that there is independent increments in it, etc. But it's one-dimensional. I remember that for me there was kind of a revelation that instead of thinking of complicated geometry, I can just think a one-dimensional random walk, which which I know. Kind of, I have intuition for it. It's something which we learn. And so eventually you take this thing, and then you compute this correlation function. Okay, or you make a displacement, and so you, and then you look at this kappa, and we kind of as a function of time. And what we found that this kind of that if you make a displacement out of it, divide by time, that would give you kappa, and it was kind of around 6. Which means that for some very strange reason, the zero vorticity line in a two-dimensional inverse cascade turbulence behave like a boundary of a percolation cluster. Now, people about percolation clusters, they knew a few things, and particularly they think, what if this is a Gaussian random field? If it's delta correlated, it's always percolation, namely that you just find a mid-level and it will be. But they say that it's even better, so you can consider this function. It's Gaussian, which means it's completely characterized by a pair correlation function. So you may say that this behaves like x in some power, and if this power larger than 3/2, I guess, yeah, it's called Harris criterion. Then it's okay. It's effectively short correlated, so you will have, in our case, omega correlation function, omega x, omega 0, it's x minus 4/3. That's a Kolmogorov scaling. And 4/3 is less than 3/2. Moreover, our field guaranteed to be non-Gaussian because it has a third moment, which is a flux. Okay? So just to check what we did, we took our random velocity field. It corresponds to a random vorticity field. Okay? And we replaced it with a Gaussian field with the same special correlations, namely with this special correlation. Immediately, this property was lost. Namely, if you look at this quantity, it's something which behaves like this. It's not a constant. It's not a random walk. This is something truly strange, which means that if you take a Gaussian field, scalar field dependent on two coordinates, build a landscape out of it, fill it by water, look at the line, which is a percolation cluster. If you're scaling, if its correlation decay fast enough, you will have a percolation property. It's conformally invariant, have all beautiful things. Our correlation function decays slower, but it has some multi-point correlation, because non-Gaussianity effectively means that we have some multi-point correlation in it. The 3-point correlation we can directly compute because it corresponds to a flux, but it has multi-point correlation, which nobody ever computed. And they somehow conspire to make your line exactly percolation line. After that, there were many properties checked. In particularly, you can look at the tangential angle, and as your curve goes, it fluctuates. So there is a beautiful mathematical theorem which tells that these fluctuations are also Gaussian, and they could be expressed in terms of kappa. And at some point, we also did this check. That's interesting, the kind of linguistic problem. So when I was learning this, I asked mathematicians, is it true that a tangent to a SLE curve angle behaves in a Gaussian way? And mathematician, a great mathematician, Phil Slaughter, told me, no, Grisha, it's such objects you talk about, it does not exist. It's a fractal curve, there is no tangent to it. And then I asked mathematical physicist, who's a friend of us both, he said, of course, you're right, this object, if you defined it, kind of smearing it a little bit, then it exists. So there are many tests that you can write with it, and it corresponds to this percolation cluster.
So with the other half scaling, with that power is still Gaussian. The tangent is Gaussian.
The tangent is Gaussian for zero vorticity line in inverse cascade of two-dimensional. Now, if we come back to this,
When you say inverse cascade,
Do you do anything to omega? Do you truncate out certain scales before you look at the zero set, or
Because it's inverse cascade, means that I have a forcing scale, and that's my minimal scale.
you just
I never look inside this scale. Effectively, I always start from like 5 times this scale. That's why all the tangents exist, and you know, it's actually a kind of a regular curve, not a fractal curve.
so do you just do a Fourier projection of the full vorticity field on just the modes bigger than the forcing, or smaller than the forcing?
The computations are done actually in a spectral way. I mean, this was Antonio Celani did in Guido Buffetta. That was, you know, back, it was 2006, which means back then it was 3 months on European supercomputer. This was heroic. It was 10,000 square. So they run it spectrally, but eventually we get a vorticity as a field. We coarse grain it on a scale of forcing, and then we look at the zero line in this case. And then we went to this whole family, because now it's interesting what actually happened to the other guys, because they are also physical models, and they all have inverse cascades. And then we check that if you look at the scaling, let's say, you ask psi of delta psi of L, it scales like L in some power, or delta V of L, you can show that it scales like m minus 1 over 3. So if you look at, let's say, this is L. So you ask, what is the Hölder exponent of velocity field? Because it now depends on the parameter of your model. Then you find out that it's just h function of m. So for n equal to 2 is just 1/3. It's Kolmogorov value. For m equal to 1, it's 0. If m equal 0, it's minus 1/3. Again, as I said, it exists and it makes sense for negative m, but there's kind of some symmetry which turns one into another. So you see really a straight line. It's a linear dependence, and you check. And of course, we checked 3/2, and we check 1/2. So there were, I mean, 3/2 is here. So it's just a straight line. So the scaling of a velocity field, of a vorticity field, of your stream function is linearly dependent on this m. And then we check if now this magic property of conformal invariance exists for arbitrary m. And we found out that, maybe I'll just, yeah, I'll show it here. So now I'm asking what is kappa as a function of m. And for m equal to 2, as I said, we have kappa equal to 6. Again, for field theorists, it's a totally magic number, because like critical percolation is kind of a simplest universality class of critical phenomena. It has a central charge equal to 0. It's something which kind of almost the simplest critical behavior that you can imagine. So for m equal to 2, for Euler equation, it's here. For m equal to 1, it's equal to 4. And 4, yeah, maybe a little bit. And 4 is another magic number in terms of random phenomena. So if you take a Gaussian free field, but with the correlation function, which is a logarithm, it's a which means that it's in 2 dimensions. So if it's correlation function h a of x, this field a, right? A of x, a of 0 behaves as a logarithm of x. It means that it's Gaussian, like it's like what it's like to call free field. So it has this probability distribution in a sense, right? And if you look at its zero vorticity line, zero level line of this field A, which is purely Gaussian, but with a logarithmic correlation function, or 1 over k squared in Fourier representation, then it has kappa equal to 4. So it is this thing which is here. And this was already in our first work, in our second work with Bernard. who is field theorist, who actually knows this stuff from the other end. And then we did a very extensive study for other things, and we found out that, first of all, this is not a straight line. It's somehow here, and then it is all the straight lines here. So in a sense, this thing behave like this. It's kind of a little bit esoteric, maybe, but this something, and I'm showing it just to show that at least one thing we were able to understand here, because all the rest look like a total miracle. Where in the earlier equation is this function, and why it corresponds to the driving with a kappa equal to 6, I don't know. I spent 3 years trying to find it out, and there are many other people definitely spent a lot of time. But this behavior somehow was kind of understood. Well, at least made less mysterious. It's all related to the fact that if now you look at the scaling of velocity, it's again, I mean, I'm returning now to the lecture number 1, and I'm trying to do Richardson, but kind of for this family. So this is how my velocity depends on the velocity difference depends on. So if I would be asking how a distance between two particles evolves, I will need to solve this equation, right? And it's L in the power m minus 1 over 3, right? So if I'm kind of back to Richardson, then this equation only makes sense when m is larger than unity. It makes sense that the velocity, it is already known Lipschitz, namely this delta v is not proportional to L in the first power, and all this, you know, but at least your velocity difference does not grow when L decreases and does not suggest you. So in a sense, it's clear that something must happen at this scale. And also this curve, one can obtain just by trying to think how actually this isoline evolves in time, and trying to find a relation with its perimeter, its let's say gyration radius. So this, if this is L and this is the perimeter, so in a sense the dimensionality is the relation between these two things, right? And now you may say that this perimeter is your gyration radius, which evolves according to this law, to solution of this equation, times number of folds, which you may assume that it grows by diffusion law. And then again, you can substitute from here how if your L, let me do it here a little bit more. So again, if I start from this law, so I have my L in the power 1 minus m minus 1 over 3 proportional to time. So I have it L3 plus 1 minus m over 3. So my time behaves as L4 minus m over 3. So this is L4 minus m over 3. And this is also L1 plus. And this gives you a fractal dimension of your object. That was kind of my way of arguing it. And then you say that it's related to kappa by formula which mathematicians derive, that your d is 1 plus kappa over 8. So you can compute this and this, and it gives you this curve. So this curve is not derived, but kind of argued that it makes sense in terms of a Lagrangian evolution. And then it tells you that when m equal to unity, you don't expect that this law would be followed. You just expect that L would just increase ballistically. So you just, as if you have a constant velocity difference, because the fact that you have velocity is a small scale field, it's irrelevant. What matters is just some kind of RMS velocity difference. And that would give you these points. So I don't want to go much into it. It's just this example shows what kind of miracles still can happen. And it happens in all this family of models. There's no theory whatsoever. Somewhere in fluid mechanics, this is encoded. And at least this partial understanding of dependence of fractal dimension on terms of Lagrangian properties of velocity is maybe encouraging. Okay, but last 10 minutes, let me kind of make a little bit overview and a summary of what I told, so that it won't be all of conformal invariance. So what we started is that fluid mechanics is essentially macroscopic science of how momentum behaves. It's essentially, I mean, when you look at Euler equation or Navier-Stokes equation, it's a momentum conservation equation. It's a macroscopic, it's continuous medium. It's supposed to not care much what is at microscopic level. It not always works. It depends on the time of observation, as we described. Everything could be a fluid, and everything could be not fluid, depending on what time you observe. And then what we discovered that when we write the equation forces, and it's particularly viscosity, for example, or pressure, then when we considered bodies, particles, billiard balls, that was it, right? But now, because V is a field, then what is written here, it's a partial derivative plus V grad V. In a sense, this is what we call inertia term. And so most of the fluid mechanics is a competition between this term and that term. And the Reynolds number measures this competition. And then what we discovered is this term is relatively simple, first order, but it's non-linear. Even when what is standing here is a linear, normal, Newtonian, as we say, viscosity, it has a form where a small parameter like Planck constant stands in front of a highest derivative. And it makes perturbation theory with respect to this term singular. And this nonlinearity, it what makes it very non-trivial. So as a result, I would think if there is a main lesson which fluid mechanics of 20th century taught the rest of physics, is it something which happens in small domain, in a boundary layer near the solid body, around the corner, at the back of your wing when you fly aircraft, extends through the whole half space to macroscopic domains. And it changes your phenomena on a finite amount, even in the limit when this nu goes to 0. Okay, that's what we like to call anomaly. And inside this wake or other regions, there is turbulence, which is a kind of classical field theory in the sense that it's a random field. It's usually what we consider in turbulence is a random field. Its statistics is not in thermal equilibrium. Its probability of any configuration in thermal equilibrium is determined usually by this configuration. If you have a Hamiltonian with a short range interaction, usually your probability distribution exponent of this Hamiltonian. It's a Gibbs measure, which means that you take any configuration, you compute Hamiltonian for it, that's your probability. It's not like in turbulence. Turbulence, there is no things like detail, but probability of your configuration may depend on the history of how you created it. So there is no surprise, and there is a lot of symmetries that you expect that are broken over there. And yet, you look at some subclass of turbulent phenomena, and all these SLA curves, etc., they have perfect Gibbs measures. They are like equilibrium critical phenomena. They're critical in the sense that it's a fractal curve. It's really have a fractal dimension. It's not a simple object, but it's really that's kind of some subset of turbulence, some sector of it, has a Gaussian statistics, at least in this class of models. And nobody has any slightest idea of why it is so and how it's actually one could argue for it. In a particular case of 2D one may say that when omega is 0, and which means that your two-dimensional velocity, where is my two-dimensional velocity? So you, because your v is grad psi, but if it's also omega is 0, that means that v is also grad phi. So you may introduce a potential, and those are Cauchy-Riemann conditions. So of course now it's any potential flow, it's conformal flow, right? Because it has both a stream function, which is imaginary, it's part of imaginary potential, and the real. And so the zero vorticity line is kind of a memory of what you would have if you would have zero vorticity in macroscopic region. I don't know, there are many speculation about it, but this is more or less the state of turbulence for today, at least from kind of my kind of particular perspective. Okay, that's more or less it for this short course. I'll be back at the end of summer, so maybe I'll read another small course. Questions?
When you talked about the encoding of the motion onto the boundary, that function, right, is in I've not worked with that before. So how does that function work? What?
Look how it works. It's really, you can imagine it's like this. So if it's constant, you can immediately solve this equation. You find out that it's just, this time it's a straight line propagate here. When it moves to the right, it turns it to the right. When it moves to the left, it turns it to the left. The faster it moves right and left, your curve does this thing. That's what.
Think of that as in time.
Time is a coordinate along this. So at some time you have this, then it kind of propagates, and this it moves. Okay. So you start from this point. This is constant, not equal to 0. So you move up. It starts moving to the right, you turn right. It starts moving back to the left, you move left. That's how it works. Of course, there are a discrete, I mean, you can live, fill it by hexagon and consider percolation on this hexagonal lattice, and then turn it into, into continuous limit. But you can also work with this pretty, it's not complicated equation. Depends, when this is some kind of simple function, you can just solve it and see. And so the faster it turns, the bigger your curve does. This Löwner piece is just a piece of genius, right? Because it really tells you that shapes could be encoded on a straight line just by the law how you turn back and forth. More questions? Yes, dear.
Has anybody studied the fractal dimension of exacted lines in the Crichton model to sort of make your heuristic?
Yeah. Well, first of all, that's what I checked, is that you kind of, that is not conformally invariant curves. About fractal lines, yeah, there were works even preceding our work on passive scalar, because you see, in a sense, there are things which are complementary. You have a zero lines, which means that you can change your omega everywhere, totally changing the behavior of correlation function. And zero line would not know about it, right? So this is kind of totally different domains of study. But there are some things that you can, but on the other hand, when you have a Crichton model and a scalar field, it's a very non-Gaussian field. Very non-Gaussian, with a very complicated. So for example, when we look at anomalous exponent of a passive scalar, and we say that they are just saturated to a constant, there's a fractal dimension of shocks in passive scalars. Right? So there's different, those are not either sets of level, but they are sets of jumps. And this is its codimension, which depends on space dimensionality. So it's a kind of, it's a very beautiful and complicated statistical geometry. Yes?
Is also another equation for closed curve?
Actually not, because first of all, this is something which is defined for the whole plane. Okay, so on the other hand, it's really, for example, when you have a very fast diffusion, namely this kappa is larger than 4, you can show that it's not a simple curve, namely that it returns to itself. So somewhere it can touch itself, right? And then it can go, and then it can touch itself again, and then it can go. So what is G about? What you actually subtract now? You subtract what is called an envelope or hull. I just didn't know. So you really go around like this. So you don't go in where you have this Swiss cheese, all your islands, etc. So in a sense, you say that so this what you map is H minus this envelope, which means that region visible from infinity. So if you have something like a finite, that's what you will see from infinity. It will be a map which would be essentially only non-trivial here and just Z somewhere far away. So in a sense, it's about curves which generally propagate unbounded, but they can touch themselves and boundary infinitely many times. You just do envelope around it. That's the geometry.
You have this vorticity equals 0 line that you get from your simulation, if I understand it. And then you apply this LL map to get the analog of C.
Yeah.
I wonder, did you have a motivation for trying that method? I didn't get the motivation for that.
Well, motivation was that if it happened to be, in a sense that what I'm doing, at least all my students now, you know, kind of, the moment they see any curve, they just check if it's SLE curve. Because then you can compute a lot of things about it. For example, for zero vorticity on Earth's atmosphere, I can predict if it enters any triangle, what is, let's say, triangle is this, what is the probability it goes to the left or to the right. It's a very powerful mathematics which stands behind it. So I just wanted to see if it happened that my curve belonged to this class. Then I have a lot of things. But in terms of understanding physics better, I didn't learn anything. So I tried. There's definitely a message here, which, but it's not, I mean, I probably won't need a mathematician of much higher caliber, because there's really some mathematical message about the structure of a flow. So technically, the fact that it belongs to this class is very, very, by the way, Shore lines, which is kind of the first example of do not belong to this class. Okay? So, but the moment it belongs, you have in some hypergeometric function give you a lot of probabilities. But in terms of deeper understanding, I don't know. I didn't know. But it's like, but the motivation, Christoph Govetsky, the late Christoph Govetsky, told me you need to learn this stuff. I say, why? When you learn, you'll probably make sense of it. It's like a new toy. So you see new toy, you want to check if it, if your toy truck also can move this way. Okay. Okay, thank you very much, particularly for persistence to be here till the end. And okay, if somebody will be around summer, I'll be back.